So in this lesson, we will be going over exteroceptive sensors. So what we hope to learn in this lesson is to identify exteroceptive sensors, commonly used in mining vehicle applications, and understand how typical range sensors function. We'll also go over different types of sensors that are available. So as you saw in an earlier lesson, exteroceptive sensors gather information external to the vehicle or machine. So for example, these could be distance measurements between the vehicle and an object, light intensity, sound amplitude, or even things like radiation measurements, temperature measurements, and so on. So the robot you see here, this is a RadBot, a radiation mapping robot, and it has a number of different sensors on it, exteroceptive sensors. On the top here, there's a sodium iodide radiation sensor used to detect gamma radiation. We have a SICK 2D laser scanner here. This gathers distance measurements. And it has a ring of ultrasound sensors here that also allow it to detect obstacles. Here we have an automated ST14 LHD. You can see it has two laser scanners in yellow here. These provide both front and back scans of the environment that the vehicle is operating in. So one of the major exteroceptive sensors used are range sensors, because we like to gather information about where our vehicle is relative to the obstacles around it. And these sensors typically use time of flight of either sound or light. So if we're looking at the distance measured, it'd be the speed of light or sound, c, times the time it takes, divided by 2, because the light has to travel to the object and return. So that's why we're dividing by 2, or the sound, if you're using a sound sensor. So there's two main types. There's ultrasound sensors. The speed of sound is typically, depending on temperature and pressure, is 343.59 meters per second. They are relatively inexpensive, but they are not as accurate as, say, a laser range sensor. Laser range sensors use the speed of light, which is basically 3 times 10 to the 8 meters per second. These are relatively expensive when you compare them to, say, ultrasounds, but the measurements are much more accurate, and for all intents and purposes, they're almost instantaneous, right? Given the high rate of speed, not rate of speed, the speed of light. So what you see in this figure is a SICK LMS 100 2D laser scanner. It has a field of view of 270 degrees. In essence, it's just comprised of a single laser and a rotating mirror that allows it to do a line scan. So as we look at this animation here, all right, as you can see, the laser light shines down onto the rotating mirror. The rotating mirror then causes the scan to sweep an arc, and you get your measurements of different objects at a given angular increment. So with 2D laser scanners, we can build fairly accurate maps of our environment. So this is a run of actually the RadBot scanning and building a map of its environment as it drove around. So here we have a lab, and then we have hallways, we have a large atrium. You can see one disadvantage of laser scanners is if objects are transparent to laser light, like windows, the scans will actually pass through it. Okay, so when you're choosing your sensors, you have to choose them based on the environment you're trying to operate in. Now if we look at ultrasound sensors, all right, they consist of an emitter and a detector. Okay, so one emits the sound and the other receives the sound. So the sound waves bounce off the object and are reflected back to the receiver, and based on the time of flight, we can calculate the distance. But as you can see, the sound is emitted as a cone. So if the object is within the cone, it will be detected. But if it's outside that cone of sound, it won't be detected. All right. Similarly, if we look on this figure here on the right, if we have an object solid object, it would easily be detected. But if we have a series of objects, the sensor will only detect the nearest object. All right, and you wouldn't be able to individually identify these different objects. Whereas if we were using a laser scanner, we would definitely be able to pick out the different objects here. So that's one drawback of ultrasound sensors. Ultrasounds can also fail in a variety of situations. If we have a soft object that absorbs sound, then we wouldn't be able to get a reflection. If obviously objects are too far away, the sound won't be reflected back. And also, if the object's at a certain angle, the sound waves can actually bounce off and head in a direction away from our receiver. And in that case, you wouldn't get a measurement of the object at all. Another type of range sensor are Kinect type sensors. People are familiar with these from Xbox game consoles. And what they consist of is we have an invisible light source that illuminates our object. It puts a grid of infrared dots on the surroundings. We then use a camera that measures the distance to each of these infrared dots. And using some software, we can actually then build a 3D depth map of our environment. All right, so that's how these type of sensors work, and they can be used in robotics applications as well. There are many other types of exteroceptive sensors. We have CCD cameras. They provide a wealth of information but require a lot more computational power to handle. We have force torque sensors. If we have a manipulator arm interacting with the environment, we can have a force torque sensor to tell us how much force we're exerting on our environment or on the arm itself. There's compasses, so we can determine heading, inclinometers, so we can determine inclination, so what angle our system is at. There are Doppler-based sensors. These are more for high-speed applications, such as highway vehicles. Proximity sensors, and even rudimentary bump sensors. These are all other examples of exteroceptive sensors.